This is a screencast video recording of a problem that was assigned for homework about links in a chain and the forces between them. I'll start here in part A, exploring the question, how much force does link 2 exert on link 1? And I note that the mass of a single link is given, and the acceleration of the whole chain is also given in this problem. And I can use my physical understanding to know that if the whole chain is accelerating with a given acceleration, each link also has that acceleration. To explore the force of link 2 on link 1, I zoom in on link 1, which I've sort of highlighted here in blue. Here's a free body diagram of link 1. Gravity acts downward on the mass of link 1, and the mass of link 1 is just ml, the mass of a link. And stronger than gravity, the force greater than gravity, the force of link 2 on link 1 is providing an upward force. So the acceleration is the combination of the forces acting on the mass. That's a statement of Newton's second law. And the combination of forces in this case is the force of link 2 on link 1 overcoming the force of gravity. The force of link 2 on link 1 minus the force of gravity on link 1. All that divided by the mass of link 1, which again is ml. Then this is just an algebraic step, multiplying both sides by ml to find that the mass of link 1 times its acceleration is equal to the force of 2 on 1 minus the force of gravity on link 1. Now I'm just rearranging this again. I guess I substituted the mass of the link times g for the force of gravity on link 1. That means that I can solve for the force of link 2 on link 1. It's equal to the mass of a link times the quantity a plus g. Going from the second to the last line was just rearranging some algebra. Does this have the units I want? Does it have units of newtons? Well, a mass times, what's in the parentheses? An acceleration plus another acceleration. A mass times an acceleration will have units of kilograms times meters per second squared, and kilograms times meters per second squared is newtons, as I want. So that's part A. Now let's talk about part B, which is to find the force of link 3 on link 2. And that's a little more complicated. And here is one of two ways to solve this problem. I'll zoom in on link 2, which I've circled here in green. And I'll make a free body diagram of link 2. If I close my eyes and empathize with link 2 and think, what are the forces that I feel? I feel the Earth pulling down with a gravitational force. I feel link 3 pulling up. And I also feel link 1 pulling down with the force of link 1 on link 2. We know that link 1 must exert a force on link 2 because of Newton's third law. If link 2 exerts a force on link 1, then 1 must exert a force on 2. So that's my free body diagram for link 2. And now here's my Newton's second law statement about this free body diagram. The acceleration of link 2 is equal to the combination of forces on link 2 divided by the mass of link 2. And again, the mass of link 2 is just ml. The forces here combine like this. The upward force from link 3 on link 2 is the prevailing force, and it prevails over the downward force of link 1 on link 2, and also prevails over the downward force by gravity on link 2. And in the denominator still is the mass of link 2. Then the next line is algebraic rearrangement. I've just multiplied both sides by the mass of a link. The line following that, this line here, is more algebra rearrangement. And then, let's see, in this line, I substitute the force of link 1 on link 2. And let's see, where did I get this value? Well, we solved the force of link 2 on link 1 in the previous slide, and Newton's third law says that the force of 1 on 2 must have the same magnitude. So the force of link 2 on link 1 was mLA plus mLg, so the force of 1 on 2 is the same. And I've also substituted here for the force of gravity on link 2. It's the mass of a link times g, the mass of link 2 times g. And the rest is combining algebraically. The force of link 3 on link 2 is 2 ml times the quantity A plus G, and so it's twice the force of link 2 on link 1. Now I'd like to answer this same problem, the force of link 3 on link 2, a different and better way. I assigned this, before we talked about Newton's third law, and it is possible to do this problem without using Newton's third law. The previous slide involved Newton's third law, but this doesn't. What if I consider that the object of interest is this red object, that is to say, links 1 and 2 together? I can kind of close my eyes and pretend to be those links together. I feel a force down of the Earth pulling me down, and I feel a force pulling me up from link 3. That's the force of link 3 on link 2 that's pulling up this red object. Do I feel the force between 1 and 2? No, I don't. If I'm this red object, if I'm this red box, I don't feel the force between link 1 and link 2 any more than I feel the force between my hip and my torso right now. It's an internal force and is not something that acts on the red object. So now I can just make a Newton's second law statement on this free body diagram. The acceleration is the combination of forces acting on the mass. That's the force of 3 on 2 minus the force of gravity on this red object, which is a joined object, all over the mass of that joined object. I do some algebra rearrangement, and then I'm down to this line, that the force of 3 on 2 is the mass of this red object times A plus the mass of the red object times G. What is the mass of the red object? Well, in this case, it's 2 times the mass of a link. I substitute, and I get the same answer as I did for the previous slide. The force of 4 on 3 and the force of 5 on 4 can be found similarly.